Yeah, so today we have Mitali. She'll be talking about hypercontractivity on HDX.
Okay. Hi, everyone. So Jeff has insisted on this seating to increase interaction. So feel free to stop me with questions. So today I'll be talking about hypercontractivity on HDX. And this is joint work with Max, Sally, and Char. Oh, not working. So traditionally, hypercontractivity has been studied on the hypercube. So plus minus 1 to the n. And so starting with Fourier analysis, discrete Fourier analysis has many applications in TCS to learning theory, probability theory, hardness of approximation, and cryptography. And in particular, hypercontractive inequalities imply isoperimetric inequalities for the hypercube. So this basically gives us a lot of insight about expansion in the hypercube graph, like which sets expand, which sets don't expand, etc. And concentration inequalities and invariance inequalities. And today we will focus on the isoperimetric inequalities part of the application. So in particular, instead of looking at hypercontractivity, which sometimes gets very technical, we will look at expansion in graphs. So what about graphs that are not the hypercube? For example, the p-biased hypercube, where you flip each coordinate with probability p instead of probability half. Or let's say slices of the hypercube, where you focus on all vertices that have k ones, some fixed number of ones. Or like these well-studied graphs called Johnson, Grassmann, and other graphs, like the symmetric group. So can we get one unified proof for expansion for a large class of graphs? Because many of these graphs have been studied on a case-by-case basis by mathematicians, and each proof requires like a lot of case analysis. So we study in this work these graphs from the viewpoint of high-dimensional expansion and give a general theory for expansion for many of these graphs, like the p-biased cube, slices, Johnson, and I'm not sure about this actually. And any questions up till now? Okay, so I'll just discuss one application. So this is like these graphs. I mean, sorry, this work is pretty new, so I don't know if there are more applications yet, but one application is to the unique games problem. The unique games problem is an important constraint satisfaction problem on two variables. And the approximation complexity, like how hard is it to approximate, is an important problem in theory. Interestingly, the characterization of non-expanding sets on the Grassmann graphs, the one graph that I mentioned previously, led to the resolution of a very important conjecture known as the 2-to-2 games conjecture. And this is a weaker variant of the unique games conjecture. And as far as I know, like this was the first time where all this really math stuff was used in TCS, like this whole theory of expansion. Using similar the same kind of characterization for Johnson, Grassmann, and HDX from this work. In another work with Dorr-Minzer, we can give algorithms for unique games. So we can now give algorithms and hardness both in different regimes using these same kind of characterization theorems. So with this motivation, let's dive into the specifics of graph expansion. Okay, sorry. So yeah, given a d-regular graph, the expansion of a set S in a subset S of vertices is defined as the fraction of edges incident on the set that go out of the set. And as many of you might know that an epsilon expander or an expander graph is a graph where all sets of size at most half have expansion like roughly 1 minus the size of the fractional size of the set. So why do we have this expression? Because if you took a random graph, then you would expect like the fraction of edges between S and S complement to be like, yeah, I mean, you would expect 1 minus the fractional size of the set to go out of the set. Sorry, is this clear? Like why we?
What is U of S?
It's the fractional size of the set. So it's mod S by total number of vertices. So if you took a random graph, this is something, it would be an expander, and it would, like, you can imagine it would be roughly this quantity. And a more complicated definition is this one. So it's G is an epsilon spectral expander if the second eigenvalue of the normalized adjacency matrix of G is at most epsilon. So if you don't know what this means, then you can think of just this definition, where we want sets of, I mean, we just want this combinatorial expansion. But we have that the second definition implies the first definition. So it's a stronger expansion definition. And so this is what an expander could look like. So actually a good expander is a complete graph. Like if you took a complete graph, this would exactly be satisfied. But in general, an expander could be something that is really sparse, but it still has the nice properties satisfied by complete graphs. And in this, your degree, like the degree of the graph could be a constant, and it could still satisfy these properties. So now what if all sets in your graph do not expand? Can we say something about special sets, for example, small sets? So we say that a graph is a small set expander if all sets S have expansion at least 1 minus mu S to the C, mu of S. So as you decrease the set size, the expansion goes to 1. But this might not say anything about large sets, for example, where the size is 1 over 10 or something. And if you set C equals 1, then you roughly get back the definition of an expander.
How should we think of C? Bigger than 1, smaller than 1?
Yeah, so you should think of C as a fixed constant, which is smaller than 1, like half or something. And a canonical example of a small set expander is the half noisy hypercube. So you have your vertices as plus minus 1 to the n. And to generate its edges, what you do is you flip each coordinate with probability half. Yeah.
Sorry, you're saying this will generate such a graph with high probability or something like that?
So this is a fixed graph. The edges are weighted actually. So at every vertex.
Okay. So sorry, so the weight is the probability of the transition.
Yeah, exactly. Yeah, so this graph, you can check that it's not an expander because if you take sets which have one coordinate fixed to 1, they will have expansion like half or something, which will not satisfy this. But as you keep decreasing the set size, the expansion goes to 1. But now, what if your graph is not even a small set expander? So can we characterize the non-expanding sets? So basically, can we say that maybe these are the only sets which do not expand?
Actually, what is the C for which the hypercube satisfies the inequality previously? Or were you going to say this?
Yeah, I was not going to say, but I can say it. So for example, I think like if you take the half noisy hypercube, then C will just be, I think C is one.
Oh.
So if you take a set,
But then
okay.
it's an expander under your
Yeah, so okay, like if you take noise to be, like if you take this flipping probability to be close to 0, like you don't really flip the probability half, then the C becomes, gets smaller and smaller. Okay, yeah, so sorry about that. Yeah, for example, in the noisy hypercube, if you take a set, in this half noisy, if you take a half size set, it has expansion half, and a 1/4 size set will have expansion 1 minus 1/4.
So under your definition for making the noisy hypercube, the epsilon expander, you make the noise to be 1 minus epsilon? Is that
Yeah. Yeah, but if the noise is something close to 0, then the C will be something also close to 0. So it might not be an expander. Okay, so what if your graph is not an expander or a small set expander? Can we say something about the non-expanding sets, that maybe these are the only non-expanding sets? So this is like a kind of not a definition, but a recent notion that has become important, called global hypercontractivity. And many graphs, such as these Johnson and Grassmann graphs, which are actually very well structured and symmetric, but they are not small set expanders. And a characterization of the non-expanding sets in these graphs was given by these two works. So the characterization looks something like this. There's a family F of induced subgraphs of these graphs, such that each subgraph in the family is a non-expanding set. So these are like the bad sets that do not expand. But every set that is not correlated with some subgraph in F has good expansion. So this characterization is saying something like, we have some bad sets, but every other set which does not look, which is not, like the union of such bad sets, or which is not, which is not like some perturbation of these bad sets, has good expansion. And we will make this notion more formal later. Okay, so let's now go formally into our results. We give such a characterization for graphs on high dimensional expanders. So we generalize the structural results for Johnson graphs to graphs over high dimensional expanders. And these capture a lot, like a large class of graphs, including the Johnson graphs and specifications of the Johnson graphs. And we prove such a characterization by showing that certain random looking sets in these graphs expand. And we take the proof of the Johnson graph and kind of robustify it to work for high dimensional expanders. So I will explain all this more formally later. Yeah.
Is a high dimensional expander also a expander in your definition of two terms?
Oh yeah, so I'll go into the that later. So first, let's look at Johnson graphs to make things more concrete. So the vertices of the Johnson graph are sets of size k of the universe of size n. And the edges of the Johnson graph with parameter nkt will be between vertices that intersect in T elements. So let's look at the Johnson graph on n equals 5, k equals 2, and t equals 1. So yeah, this is not a picture I have drawn. So each vertex is a subset of 5 elements. So the red dots are indicating that, for example, if we label this as 1, 2, 3, 4, 5, then this set is 4 and 5. And so each vertex is a subset of size 2 of the universe of size 5. And we have edges between, for example, this vertex and this vertex because they intersect in this element. Yeah. Exactly T. Wait.
Drawing it between two sets of data intersecting exactly T elements. Exactly.
Yeah. Oh wait, is it not correct?
The
Okay.
graph is fine. It just doesn't connect.
Okay. Okay. So is this definition clear? Okay, cool. So now let's look at why the Johnson graph is not a small set expander. By looking at, so we'll just look at this version where we have the nk k by 2 element, t equals k by 2, or we also call it the half noisy Johnson graph. So half is because k by 2 divided by k is half. And this graph is the following. At every vertex, we flip, so every vertex can be thought of as a k subset of n. And to generate an edge, we flip every element with probability half. Okay, so this is like approximately jn k by 2. Yeah, this is one way to view the jn k by 2, or you could also flip exactly half of the elements if you wanted. And now let's look at some subsets of this graph which do not expand. So let's look at S1 to be all the sets that contain the element 1. So S1 is the set of subsets that contain the element 1. And we can see that S1 divided by the size, so the fractional size of S1 is k over n. Like this is just like by calculation, or roughly you can choose any elements. So it will be something like n minus 1 choose k minus 1 divided by n choose k. So it's k over n. And if we think of, we will always think of k as a constant and n as growing. So this is going to be little of 1. But now we can quickly see that the expansion of S1 is actually exactly half. Because what's the probability that you flip? So the only way you can go out of S1 is if you flip the element 1, and that is flipped with probability half. And then similarly, we can consider the set Si to be the set of subsets that contain, sorry, not contain elements 1 through I. And a similar calculation shows that this set is of size k by n to the I. So it's again of size little of 1. And this expansion is 1 minus 1 by 2 to the I. So if you go out of the set only if you flip any one of the elements 1 through I. So in fact, like if you did the half calculations for half noisy hypercube, the expansions would be the same. Like you can define analogous sets and you would get the same expansions, but the set sizes would also be constant instead of little of 1. Yeah.
What do we want these expansion parameters to be to call it an expander? Like arbitrarily close to 1? Or
Yeah, so the expansion parameters are going close to 1, but the set sizes are still little of 1. So we would have liked, yeah, so that's my next point. We can see that the expansion of SI is not arbitrarily close to 1. It's not of the form 1 minus the fractional size of SI to the C, because the fractional size of SI is little of 1. So it's not like 1 minus little of 1. It's some fixed constant. Whereas in the noisy hypercube, we had this inequality. So now we see that this graph is not a small set expander. And then KMMS showed that, in fact, these are the only obstructions to small set expansion. Sets that are not correlated with these I restrictions. So any of these, generalizations of the sets SI, they have expansion 1 minus 1 by 2 to the I plus 1. So an I restriction has expansion 1 minus 1 by 2 to the I. And if you're not correlated with the ith level, then you'll have expansion, which is the next level. So 1 minus 1 by 2 to the I plus 1. And the downside of this proof is that it's really catered to Johnson graphs, which are highly symmetric and have some nice properties. So we generalize this result to high dimensional expanders. So the high dimensional expansion provides a general framework to study like these set system kind of graphs, like Johnson and Grassmann and p-biased cubes. And it's led to many recent breakthroughs in approximate sampling and coding theory. And we have to overcome some technical issues, like high dimensional expanders can be much more asymmetric and sparse and far from products. So for example, if you look at a complete graph versus an expander, it's not really clear that a proof for a complete graph would go to an expander, because the expander could be sparse. So similarly, HDX could be sparse versions of Johnson graphs. So we introduce a new explicit Fourier basis for high dimensional expanders, and also a local to global method for analyzing higher moments. So now finally, let me tell you guys what are high dimensional expanders. So instead of viewing, let's focus on the Johnson graph. Instead of viewing it just as a graph, as like, vertices and edges, we view it as a complex. So consider, think of always this hypergraph as the Johnson graph to be concrete. And let's say we have the vertices of the Johnson graph, which are actually all the subsets of size K of n. So then using these subsets of size K, we generate the following complex. So let's focus on n equals 4 and K equals 3. We have sets of size 3 of the universe of size 4. We take all these sets and then take all the subsets of size 2 of every set. Then we further take the subsets of size 1. And the final thing is phi, which is an empty set. Yeah, and we could start with any hypergraph H instead of all subsets of size 3. And now we just draw edges by inclusion. So phi is included in 1, and like so on. Like 4 is included in 1, 4, etc. So now we have this whole complex. And now we will define like, special sets on this complex and random walks on this complex, which basically generate Johnson graphs and many other graphs. So let's define these special sets called links. So for example, look at the link of 1. So we just take the vertex 1 and look at everything that contains 1.
Can I ask you some clarifying questions?
Yeah.
So just to understand, you started with a K-uniform hypergraph, and then you, for every K set, you added all possible subsets of it.
Yeah, exactly.
So now I have like a hypergraph with like sets of all possible sizes, K, K minus 1, and so on.
Yeah. So we look at it as a complex, which is like with these levels.
Okay. So by complex, you just mean.
Yeah,
like,
this whole object is called a complex.
So okay, very good. So a complex. So if I want to get a complex of a hypergraph, I just classify the size of the sets.
Yeah.
K size sets and K minus 1
Yeah.
sets and so on.
Yeah.
Together with the edges, and the edges always go only between adjacent levels.
Yeah. So we are looking at this. Firstly, this simplicial complex where we are we have like all the levels 3, 2, 1, everything.
Yes.
And yeah, we are looking here at only edges between complex.
Okay. So if I forgot about the fact that this came from a hypergraph with like downward closing, then I could have just called it a graph. Because there are vertices and there are edges.
Yeah, but we will look at graphs generated in a different way. So we won't look at a graph which is like all of these as vertices and these are the edges. Yeah. So remember, like we are trying to generate the, for example, Johnson graph, where the top level is the vertices and edges are between sets that intersect in one element, for example. So firstly, let me define what is a high dimensional expander, and then I will define how do you get the Johnson graphs and other graphs. So we look at the link of any element in this complex, where we take any element and take the complex induced by the element, like the upward part of it. Like for example, the orange thing indicates the link of 1. And now, for example, in this picture, this is just a regular graph. So these can be thought of as vertices, and these can be thought of as edges. So for example, actually, let me say a simpler thing. If you look at the link of phi, that is just the whole complex. And the first 2 levels just are a regular graph. Like you can think of 1, 2, 3, 4 as vertices, and 1, 2, 1, 3, 1, 4, etc. as edges. So the first 2 levels of any complex are a graph, and we can look at the expansion properties of that graph. Similarly, we can take any subcomplex and look at the graph in the subcomplex. So here we look at the link of 1, and that is the complete graph. Is that any questions on that? So we are looking at these as vertices, but they all contain 1, so you might as well ignore the 1 part of it. And these are 3 subsets, but you can think of them as 2 subsets.
So the link, so what is the type of link? Like, is it a hypergraph? Is it a graph?
So the link is the whole complex, but if you look at the first 2 levels, that will just be a graph.
Because you're drawing only
Yeah.
levels here, right?
So it's a whole like up to x of k, but here I've drawn only up to x of 3. And if I look at the first 2 levels of the link of 1, then it is just a graph, and I'm ignoring the element 1 in all of these things, and I'm writing it as a complete graph. So example, if you look at the link of phi and look at the first 2 levels of the link, we will have vertices which are 1, 2, 3, 4, and edges will be 1, 2, 1, 3, 1, 4, 2, 3, 2, 4, 3, 4. So you'll get the complete graph on 4 elements. So now actually, if you look at, if you took this complete complex, like where you have all possible vertices and then take their downward closure, you will, if you look at any link, it will always be the complete graph. Like the graph over the link. And then this motivates the following definition, like a graph is a complex is a high dimensional expander if the graph associated to every link is a good expander. So this is a notion for the whole complex. And then if we have this notion, then we get some nice properties that we'll see later. So an example, if we took the complete complex, you can quickly check that every graph associated to every link would be the complete graph on n vertices, or like if this was like 1 to n, and the complete graph is a 1 by n local, like the second eigenvalue is 1 by n. So it's a really good expander. So in some sense, the Johnson graphs are like the complete versions of high dimensional expanders.
Wouldn't this complex contain some small links that were worse expanders? Like
this particular complex?
Or the complete complex would have some links that were graphs on like 3 vertices or something, which would not be particularly good.
Oh no, you wouldn't get.
Well, then wouldn't we bottom out at 1 over k then, not 1 over n?
Oh no, you won't have it on k. You will always have n. Like think of this as 1, 2, 3, 4 up till n.
Right.
Like you.
Okay, so what I'm saying is, say we take the link of a set that's like everything in the graph except for 3 elements, right? So it's a very small complex.
Yeah, but you would still have, I think.
Wouldn't it have 4
Oh yeah, so we are not going up to level k,
okay,
level n. So
all
you're only
links
going up.
that aren't too close to n.
Yeah.
But k is a constant in this way.
Yeah,
So
yeah,
we think of k as a constant.
Yeah.
So it's always at least 1 over n minus k, right?
Yeah.
Okay, so we're only looking at the first k levels. Of
Yeah.
this. Okay, thank you.
Yeah, sorry. So it should be 1 by n minus k. Okay, so any questions, any more questions about this? Yeah, so this is like basically some notion of high dimension, like generalizing expansion to high dimensions. And now we can finally talk about how to get graphs over these complexes. So what we can do is, let's say we wanted graphs over X, or like the third level. So we wanted these as vertices of our graph. Then how do we generate edges on these vertices? What you can do is start at any vertex and take a random walk in the complex. So like fix the random walk to go down 2 levels and come up 2 levels. So you start at any vertex and you take a random, so start at this and you take a random edge from these 3 edges. Then you take a random edge going down, and then now you're at 1, and then you take a random edge going up and a random edge going up, and that will get you back to the top level. So you can do this and like generate, for example, the Johnson graphs. So yeah, let's look at yeah, so just let's see why you can generate the thing where you intersect in one element. So if you just took 1 step down and 1 step up, you would either go back to the same vertex, but with very low probability. But mostly you will go back to a vertex where you will intersect in all but 1 element. And then if you want to intersect in like k by 2 elements, you go down k by 2 levels and go up k by 2 levels. So instead of viewing just edges between graphs, like edges between the top level, it's very useful to view like these edges as actually generated from these random walks that go up and down a complex. Okay. So what's the characterization that we get for these random walks? So every random walk corresponds to a graph. And we can prove that links are the only non-expanding sets in these like these graphs that we discussed, which go up and down a complex. So links are the like the generalized analogs of restrictions on the Johnson graphs. And so we say a set is pseudo-random if it's not concentrated in any link. Like if, so we know that links are non-expanding. So we don't want a set to be concentrated. So if it's I comma epsilon pseudo-random, if the density of the set inside any link is at most epsilon. So it's in some sense random looking. And every set that is not correlated with any I link has the expansion of an I plus 1 link. So if we look at like this half lazy walk, which goes down half of the levels and then comes back up half the thing, we get that every set S has expansion 1 by 2 to the I plus 1, minus some error, which depends on I and the spectral parameter gamma.
What is the notation?
Yeah, actually, I didn't define this notation, but it means that so we generate this graph by going down and up. And then now we have just a regular graph and look at the expansion of any set S. Yeah.
Just to clarify, by pseudo-random, we're not saying anything about its like predictability by general function. We're just talking about how it correlates with links.
Yeah,
It's not
yeah,
like a cryptography.
yeah.
I guess it behaves like a random set if the only tests you had was intersection with the links.
Yeah.
Okay.
Yeah, so this is again like this 1 by 2 to the I plus 1, which pops up in many places. Like if you take the expansion of a half noisy hypercube or a half noisy Johnson, then it's 1 by 2 to the I plus 1. But now we get it for all sets that are pseudo-random. So we don't get it for all sets. And this proof goes via hypercontractivity. And as I said many times, it generalizes the Johnson proof. So I'll just give a like very quick overview of the proof. So firstly, what is hypercontractivity? It's an analytic tool to prove these expansion properties in graphs. So instead of analyzing only sets on graphs, we analyze like general functions defined on the vertices of a graph. And it implies not just like expansion properties, but also concentration and anti-concentration inequalities. Yeah, and for example, on the hypercube, it implies results like what are the structure of the sets which are non-expanding, like Ryan's result on majority stablist and this Bourgain-Kalai result. So like a one-slide crash course on Fourier analysis. Every function on, let's say, on the hypercube to the reals can be written as a polynomial, multilinear polynomial. And just think of f as like this. We break down the function into these levels where like the levels go from 1 to n. So each f can be written as a sum over fi, where each fi we call it of level I, or it actually on the hypercube it has degree I in these variables xi. And this decomposition, we can show it has some nice properties, like all these functions are orthogonal to each other, like functions from different levels. And if we look at the hypercube matrix, then like the adjacency matrix, then these FIs are eigenvectors of the matrix. And the important property is that usually that C1 is equal to 1 and C2, etc. These are like strictly decreasing. Now, the very nice lemma proved by Bonami says that low degree functions, or like these FIs for constant I, they are smooth in some sense. So it shows that the L4 norm of Fi is at most like some constant, which is exponential in I, times the L2 norm of Fi. So for example, Fi cannot be very concentrated on a few vertices of the hypercube. Like it cannot be something like have a few ones, like the function the function Fi cannot assign a few vertices to be 1 and everything else to be 0. Because in that case, the L4 norm would be much larger than the L2 norm. So it's saying that the functions Fi are like well spread out across all the vertices. And in fact, this lemma is not so hard to prove. It follows by like expanding out things and doing the right induction. And like this lemma implies small set expansion for the noisy hypercube. So roughly the intuition is that we know that FIs cannot be very concentrated on a few vertices. So small sets, like if you look at the indicator function of a small set, it cannot be like one of these FIs. It has to be on a larger, like Fj, where J is much larger, like J is non-constant. Like J depends on the size, 1 by the size. And basically these FIs, like if you're concentrated on the larger levels of the hypercube, then you have good expansion.
So what C would you get as a function of the eigenvalues CI?
So actually, if you just use 2 to 4, then you won't get the optimal C for half noisy. But in general, like for half noisy, you should use some like 2 to Q hypercontractivity to get like C should be 1, as we discussed earlier. Basically, for half noisy, like you can recover that. It's yeah. So basically, proving this kind of inequality for the low levels of the decomposition gives you expansion on a graph. So we define a similar basis for the high dimensional expanders. So we look at functions which are from the kth level to the reals, and they can be written like they can be decomposed into sum of Fi, where each Fi is like, instead of degree I, now it's like level I. It somehow corresponds to the ith level of the complex. And these Fis now do not form an exact eigenbasis, but only an approximate eigenbasis. So Fi dot Fj is approximately 0. And if you looked at like any of these random walks which we discussed, like which go down, up on the complex, and thought of them as H, then H Fi is like approximately Ci times Fi.
So I have another question just to make sure I understand this right. What does this mean? Ci dependent only on walk H?
Yeah.
And what else could it be on the function?
Yeah, exactly.
No, but F is a vector. So the type is like H is being applied to a vector and you're getting a scaling of a vector. Yeah,
but it could have depended on like the function in some weird way, right?
Fi is a huge class of functions, and it's saying they all have the same eigenvalue.
Fi is a class of function. I thought Fi is a single function.
So if you look at a particular function F, it can be decomposed into sum over Fi, and Fi's like come from a class of eigenvectors. Like they're basically eigenvectors.
So in the country hypercube, I think of Fi as all degree I polynomial.
Yeah. But it could be any multiple, I mean, different combinations of the. And yeah.
The basis is not just like some version of the p-biased Fourier basis?
Oh yeah, it is some kind of version of it, but you have to define it for HDX and stuff.
Oh, I see, because I may not have one possible case that's
Yeah. It's this, yeah, Efronstein, like some analog of that. And then, yeah, I will not go into the proof, obviously, but this is the theorem that if a function is pseudorandom, so we define that what it means for a set to be pseudorandom, but we generalize that notion to a function being pseudorandom. And if a function is I comma epsilon pseudorandom, then you can prove the same inequality, like Bonami type inequality, that the L4 norm of the function is at most exponential in j times the L2 norm plus some error parameters. But this does not hold for all level j functions, but only the pseudorandom ones. And like again, using this classical connection between hypercontractivity and expansion, we get that all pseudorandom sets expand. And I will end with like a cute lemma that, or I don't know if there's enough time or not, but like okay, Pravesh is saying yes. So I'll just end with like a cute lemma that we use. And actually it's like a lemma on graphs. I mean, we generalize it to HDX, but yeah, so as I said, old methods relied on like product structure. So for example, if you pick V1 to Vk from the vertices of a Johnson graph, this is close to the distribution if you picked V1 from N, V2 from N independently. So these methods rely on this property. And HDX could be very far from product. So for example, if you picked like a K set from the top level, you could have the probability that the N first element, for example, is 1 by N. But given that the second element is 2, the probability that it is 1 is very large because it's sparse. But the key idea is that HDX is like close to product on average. So let's, so I'll like illustrate this small example where we can think of it as something on graphs, like expander graphs itself. So for example, think of x1 as vertices and x2 as edges. So if you pick a vertex in a graph and let pi v be the conditional distribution on the edges that contain the vertex, then the global and conditional expectations on f on the vertices are close. So what do I mean? So like actually I'll just draw it here. I don't know if people can see. Like if you had a graph and you took like suppose it was an expander, then if we took expectation of f over all the vertices, versus you took any vertex v and took its expectation only over the neighbors of v, then these two could be very far apart. But what we can do is like relate them by this gamma matrix, and on average over v, these two expectations will be close. And in fact, like this is a very simple proof. So we just expand it out. Like expectation over this, let's say this distribution where it's over, let's say uniform over the neighbors of V versus uniform over the whole graph. We have this uniform over just the neighbors of V, we just have probability that W conditioned on the vertex V times f of W. Like, so this is f of W. Was minus like probability of W times f of W, where W ranges over everything. So probability of W condition on V is just the transition probability that you go from V to W.
Are you using
In the
similarity?
No, so we can, yeah, so I was just saying uniform and stuff, but it's actually like for any distribution over the vertices. We'll finally use that the graph is an expander. Yeah, yeah, yeah. So probability that W condition on V is just the transition probability of V to W in the graph, like this X1, X2. And this thing can just be seen to be like the adjacency matrix of G applied on the vector F and evaluated at a particular point V. Like the adjacency matrix at any entry is just probability that you go from W to V. Sorry, V to W or something in undirected. And now, so we know what this means. And now what does the second expression mean? So like you can even think of this as uniform, like probability of W as uniform for simplicity. We would just get that this would be just the expectation of F, and pi would be just the matrix where you just have all entries are 1 over n. And combining, we get that this is AG minus pi applied on F and then evaluated at V. But AG minus pi is like literally the at most the spectral norm, because pi is like 1 transpose. So that is at most gamma if the spectral norm of the graph is gamma. And then on average over V, like we just use that the spectral norm is at most gamma to get that this quantity is at most rho of gamma. Okay, I guess I'll just mention like 3 open problems. So we gave it for simplicial HDX, like where we have all the levels. So this does not give a proof for the Grassmann graph, and maybe there's like more to be discovered where you have not all the levels, but like still have these expansion properties. And yeah, so there should be more applications of this to like complexity theory and algorithms and other areas. Thanks.
So you need the top eigenspace of the random mark to have a small 2 to 4 norm.
So not in the proof. So sorry, in this proof, we just need it to be at most gamma. Like these are the like this kind of lemma we use to analyze the 4th moment to show that it's smaller than the 2nd moment.
Oh, so okay.
But these are the key lemmas which are required to like not rely on product structure, like kind of de-randomize the earlier proof for Johnson graphs. Like we have to analyze 4th moments,
Right.
but to do that, like we need these kind of lemmas, basically. But this works without any 4th moment thing. So this is just spectral norm of the matrix.
But
Wait,
like,
what was your?
Maybe I can ask.
Oh,
you.
yeah.
So can you think of the result as giving an explicit basis for special?
For spectral,
Let's say just two uniform. I think as Professor mentioned, with no explicit basis there for P bias, things are very explicit. I don't think we know such a basis for standard.
oh, yeah, that.
Maybe not just the no, they will just use the identity vectors of the graph. It's not explicit. But I think even here that would happen if I'm getting it correctly. Your basis would be HDX dependent, right?
Yeah,
It can't
yeah.
be reversal in it.
Yeah. It's like given the HDX, it's some basis for the HDX.
So is it correct? Just to answer your text question and check that I understood correctly. Is it the analog of eigenvectors for graphs?
Yeah, but like specific thing which we can write down given the HDX. Like I think for an expander, you do get a approximate basis also. Yeah, I could. Yeah.
It's not eigenvector based.
Yeah, so it won't be like exact eigenvectors, but it'll be approximate up to this gamma term. Like, so given the graph, you can just write down what are the entries of the eigenvectors. approximate eigenvectors.
I see. Okay, so I agree. Okay, this is curious. We can maybe.
Yeah. Yeah.
So this works for any gamma HDX.
Yeah, 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 but we require this gamma parameter to be really small, which is an issue. Like if you want k to
Well,
be,
for effective Johnson graph, it doesn't matter.
yeah, but not if you take k to be like log n, like more than log n or something, because of this parameter. Yeah.
Yeah,
Okay.